We're going on with the study of area of planar regions, but now using a technique that is called horizontal slicing. So just to review what we've seen previously, we've talked about finding the area of a region that is bounded below by a function y is equal to f1 of x, above by a function y is f2 of x, on the left by x equals a, and on the right by x equals b. And we've seen that using a Riemann sum, we could come up with a formula, the integral from a to b of f2 of x minus f1 of x dx, which is most commonly stated in its memory aid version as the integral from a to b of the top function minus the bottom function of x. This is commonly referred to as vertical slicing. And why is it called vertical slicing? It's because if we imagine drawing the rectangles that are necessary for the Riemann sum, those rectangles are vertical. Their longest edge is a y edge, and their smallest edge is the delta x or the dx edge, which is along the x-axis. So the same region can often be thought of in a different way. If we take a look at the diagram that is down on the right here, if we relabel our areas, if we can consider this same region by being bounded on the left by a function x is equal to g1 of y. It's bounded on the right by a function x is equal to g2 of y, and below by y equals c, and above by y equals d. So if we do the exact same exercise, which we're not going to go through here, but we can imagine this, we could draw rectangles through this region, but we would draw those rectangles horizontally. And setting up a Riemann sum using these rectangles, well, in this case, the delta y is going to be the base of the rectangle, and the height of the rectangle is going to be the difference between those two functions. And if we want that height to be a positive value, if we want that to be a positive height, then we're going to take the greatest value, which is the rightmost value, or g2 of y, minus the leftmost value, which is the lowest value, and it is g1 of y. So without going through the exercise precisely, we can imagine that a formula using Riemann sums could be developed that would end up by giving us the area of this region as the area from C to D of g1 of y. Let's change those. g1, g2 of y, the rightmost value, minus g1 of y dy, which is said in its sort of most memory aid type way of the integral from c to d of the rightmost function minus the leftmost function with respect to y dy. And when we set up an integral with respect to y to find an area, this is called horizontal slicing, again because the rectangles that would be drawn to create the Riemann sum are drawn horizontally. So a reasonable question to ask would be, why bother? Why do we want to do this? If we look at the diagrams up here on the right, it looks like they're fairly equivalent. Expressing with respect to x or expressing with respect to y is not going to make a big deal of difference. But as we're going to see in the exercises below, there are some areas which are going to be a whole lot easier to evaluate if the region is expressed in terms of boundary curves that have y as the dependent variable. So let's go ahead and scroll down to the first exercise. So number 1 here, we're being asked to consider the region R bounded by the parabola x is equal to minus y squared plus 10, and x is equal to y minus 2 squared, which can be expanded y squared minus 4y plus 4. Firstly, we're being asked explicitly to sketch the region R and to find all the points of intersection. So that means we have to remember how to sketch parabolas that are expressed in the form x is equal to g of y. So they're already solved for x. X is a function of y, and so we have to use our tools for sketching that type of form. So the first thing to do is maybe look at the coefficient. The coefficient of the y squared is -1, which is a negative value, which means that the parabola faces the negative values. The negative values in the horizontal facing parabolas are on the left side. So this parabola is facing left. An interesting way to maybe get a handle on where the parabola is placed is to find some intercepts. So for example, if we let y equal 0 to find the x-intercept, then we're going to see that x is equal to 10. So the x-intercept is when x is equal to 10. Let's go and put that on the graph. The y value, or the y-intercept, so if we let x equal 0, right? So if we let x equal 0, then we're going to get y squared is plus or minus root 10. So root 10, I'm not going to pay a whole lot of attention to scale. Let's just put two values into there. So root 10 and minus root 10, and that parabola, knowing that it faces left, well, we've got enough information to give a decent sketch of that parabola. So there is our parabola. X is equal to minus y squared plus 10. Okay, so let's do the same exercise for the other parabola. I'll switch colors here in red. And we see that the leading coefficient of the y squared is 1, which is a positive value. So this faces the positive direction, and when we're talking horizontally, that positive direction is right. So this parabola is going to face right. We can do the exact same trick for the intercepts here. If we let y equals 0. So if we let y equal 0, then we are going to have x is equal to minus 2 squared, which is 4. So x is equal to 4 is maybe about here. And there is the y value. When x is equal to 0, then we have y minus 2 squared is equal to 0, and there's only one value that will do that, and y is equal to 2. So here we have this. That, incidentally, is going to be the vertex. That is in vertex form, that parabola, and so we know it faces right. That's enough information to sketch our right-facing parabola. So the region that we are asked to find is the region bounded between the two. This is our region R in here, and so that's the region that I'm highlighting or outlining here in gray. So that is going to be our region R. So we're asked to find the points of intersection. Well, we can see here that there are two, and so we're going to find those using the comparison method. So we're going to set the two values equal. So if I call this x1 of x and the x1 of y and call the second value x2, I can set x1 equal to x2 just like you would in any problem where you're trying to find the points of intersection, the comparison method. You can set values equal. I'm going to use the expanded form of the parabola on the right given there. So I'm going to bring everything over to one side, so that will leave me with 0 here. I will have 2y squared, so 2y squared minus 4y, and 4 minus 10 is minus 6. I'll factor out a common factor of 2, and that leaves me with y squared minus 2y minus 3, which factors for us very nicely. So 2 stays on the outside, y minus 3, y plus 1, which is telling me that y is positive 3 or y is minus 1. So that seems to fit pretty well with the diagram that I've made here. So that looks like we've got y values at minus 1 and 3, and the only thing left to do is figure out the x values so that we have the full coordinates of the point of intersection. So we're going to plug back into one of the formulas. It really doesn't matter which one, so let's plug into the formula here. X is equal to y minus 2 squared. So if x is equal to y minus 2 all squared and y is equal to 3, then we get 3 minus 2 squared, which is minus 1 squared, which is 1. So that looks here like we have an x value of 1. And again, don't worry about my scale. At least 1 is to the left of 4, so we're okay as far as that's concerned. And then lastly, over here, the last value that we have is y is minus 1. And so if x is equal to minus 1 minus 2 squared, that's minus 3 squared. That is going to be 9. And so this point here will have x coordinate of 9. So our points of intersection are the points 1, 3, and the point 9, minus 1. Moving on to part B of the question. Set up the integral or integrals required to calculate the area of R by horizontal slicing. And horizontal slicing is, of course, telling us that our rectangles are horizontal, and so it is going to be an integral with respect to y, so dy. So I've gone ahead and copied our region back down here, and horizontal slicing, that means we are drawing our rectangles horizontally. So we're looking at left boundary curves and right boundary curves. And I want us to notice that no matter where in the region we draw our rectangles, that the right curve is always the parabola in black, and the red curve is always the left curve. So if we are going to try and apply our formula, the integral from c to d of the right curve minus the left curve, we have enough information in our diagram already to go and write out the integrals. So we know the c is the bottom value here, so our c is minus 1. D is the top value, so d is 3. The right curve is the parabola x is equal to minus y squared plus 10, and the left curve is the parabola y squared minus 4y plus 4. So I can go ahead and write those in. So minus 1 to 3 of the right curve, so minus y squared plus 10, minus the left curve, y squared minus 4y plus 4 dy. And if the question said set up and do not simplify or anything, then we could leave it as it is, but why don't we just go ahead and do a little bit of a simplification here. So if we multiply this negative sign through into the parentheses, we're going to get minus 2y squared plus 4y, and 10 minus 4 is going to give us plus 6 dy. And since the question says do not evaluate, we'll leave our answer there. Going on then to part C. Set up the integral or integrals required to calculate the area of R by vertical slicing. So by vertical slicing, we're talking about drawing rectangles who have their base as a dx or a delta x. So we want our functions to all be expressed in terms of x, which means that we have a little bit more work to do here. We've got to take each of these parabolas and express them in terms of y as a function of x. So if we take the first parabola, which is the same as up here, I've just written it in its factored form, and we try and solve for x, so we're going to get, so if x is y minus 2 squared, then plus or minus the square root of x is y minus 2, or y is 2 plus or minus the square root of x. So we have two functions here. So what is that telling us on the curve? Well, the positive here, the positive root, that root function is going to be the top of the parabola. Let's go ahead and change the labels here. So that is going to be 2 plus the square root of x. And the bottom root, so the root down here, that root is going to be 2 minus the square root of x. So we're going to do the same thing for the other parabola over here. So let's go ahead and do that. If x is minus y squared plus 10, then y squared is 10 minus x, and y is plus or minus the square root of 10 minus x. So again, we have two root functions. The parabola in black becomes two roots. So let's go and write this one in green. That is again the positive root. So that is y is plus the root of 10 minus x. And then what color were we missing? How about a nice yellow? So this root down here is going to be y is negative, oh, the yellow doesn't show up so well, hey? Negative the root of 10 minus x. And then if we're paying really careful attention and we imagine drawing our vertical slices or the rectangles which we'd use for our Riemann sum, we see that those rectangles have different bottom and top boundary curves depending on where in the region we draw them. So in fact, we've got three distinct regions. We've got a region here which I'll call region 1, where the rectangles would go from the blue curve to the pink curve. We've got a region in the middle which I'll call region 2, where the rectangles would go from the blue to the green, and then region 3, where the rectangles would go from the yellow to the green. If we want to know the x values that delimit each of these regions, well, we just read the x coordinates that we have already on our graph. So from 0 to 1 gives me region 1. From 1 to 9 gives me region 2. And from 9 to 10 will give me region 3. So I want to use our vertical slicing formula, which is going to be the integral from a to b of the top function minus the bottom function. And I'm going to do that for each of those regions separately. So the region that I've labeled 1, so the region is from 0 to 1 of the top curve, which is 2 plus the square root of x, minus the bottom curve, which is 2 minus the square root of x, top minus bottom, dx, plus the second region's integral. So that's going to be the integral from 1 to 9. The top curve is now the curve in green, so that is the root of 10 minus x minus the blue, so minus 2 minus root x dx. And finally the third region goes from 9 to 10, and we've got the green curve, which is the root of 10 minus x minus the yellow curve, which is minus the root of 10 minus x, all of that dx. So again, if you were told just to set up, not to simplify, you could leave it like this, but let's clean this up a little bit here. So these 2's, if I multiply through the negative sign, the 2's are going to cancel, and I'm going to get minus minus, so I'm going to add the two roots. I'll get 2 times the integral from 0 to 1 of root x dx, plus in here, there's not a lot to clean up in the second integral, the integral from 1 to 9 of the root of 10 minus x minus 2 plus root x, And then lastly, the integral from 9 to 10. The same thing, those minuses are going to cancel, so I'll squeeze in the 2 out there. The roots of 10 minus x dx. And that is the expression of 3 separate integrals, the sum of 3 separate integrals that would give us the area of R calculated by vertical slicing. So finally, part D, which of B or C would be easier to evaluate? Well, I think the answer is pretty clear that the integral in B would be easier. 1, it's a polynomial, so B is easier. Y, 1, it's only polynomials, no root functions. And 2, there's only one integral instead of 3. And so clearly using horizontal slicing, although it's perfectly possible to find the area of this region by vertical slicing, the area calculated by horizontal slicing has some definite advantages.